Watch this. Thanks to physics, I can perform a magic trick. I will make this glass vibrate using only my voice. Today, I will talk about 3 connections between this phenomenon and our SPH 3U course. The connections are to the work, energy, and power, and sounds and wave units, specifically to the law of conservation of energy, resonant frequency, and acoustic lessons we have learned in Units 2 and 4. First, let's explain how the law of conservation of energy applies to this phenomenon. It begins with the straw containing gravitational potential energy due to it bouncing on top of the glass, as well as the chemical potential energy within my body from my calorie intake throughout the day in the form of food. My body's chemical potential energy is converted into electrical kinetic energy because of the human body's neural pathways, which allow me to vibrate my vocal cords at my desired pitch. The vibration of my vocal cords creates kinetic sound energy, which vibrates the air around the glass at its resonant frequency, causing the rim of the glass to oscillate and vibrate the straw that is balancing on it. The vibration of the straw causes it to bounce against the rim or roll off and transform the sound energy into mechanical kinetic energy, due to the gravity pulling it down onto the table as it falls off. Other applications of the law of conservation of energy are hydroelectric power plants and cars. Hydro plants convert the gravitational potential energy of dams and waterfalls into mechanical energy to turn the turbines in a generator and collect renewable electricity. Gas-powered cars use the chemical potential energy in fuel. Through combustion, it is converted into thermal energy and mechanical energy, causing the wheels to turn. Now let's elaborate on the resonant frequency. The specific resonant note of this wine glass was C5 sharp. Its frequency in hertz is 554.37 hertz. All matter has a resonant frequency, or multiple resonant frequencies, because all atoms have their own resonant frequency. When I sang the resonant frequency of the glass, the standing waves produced a constructive interference, which increased the amplitude to the point where the glass began vibrating. The resonant frequency of materials is something that engineers have to take into account when designing any complex structure or vehicle, like a bridge or plane, so that the resonant frequencies of the designed structures cannot be amplified enough to cause any harm to the people using them, like this glass has been able to in order to drop the straw. Applications of resonant frequency are in MRI and Bluetooth technology. MRI technology uses resonant frequency to take pictures of the hydrogen atoms in different tissues, organs, and bones in our bodies. Bluetooth technology works by communicating between devices at a frequency of 2.4 to 2.4835 gigahertz. Finally, let's discuss the acoustics of my basement, the room where these clips were filmed. My basement has very little furniture, so the reverberation time is extended, due to there being less objects to absorb the sound waves, resulting in an echo which changed the pitch of my voice slightly before it hit the glass, causing the frequency I sang to be slightly different than the resonant frequency of the glass. Increased reverberation decreases sound quality, requiring me to sing louder and longer to affect the glass, as opposed to if I had done this experiment in a padded closet. Other applications of acoustics are auditoriums and recording studios. Generally, auditoriums aim to have 1 to 2 seconds of reverberation time to allow people sitting anywhere in the auditorium to have an enjoyable experience of the performances, whereas recording studios aim to do the opposite. The goal of a good recording studio is to have soundproof padding, which allows the musicians or singers to record their audio without outside interference and distortion of the frequencies they produce. In order to achieve this, recording studios are usually within another room, so there is extra absorption of outside noise, like traffic. Test question. Let's create a real-life example of resonant frequency. In a 25.0 degrees Celsius room, a 19.0 centimeters wine glass vibrates due to a tuning fork, with its resonant frequency being hit and held at the 9th harmonic directly on top of the glass. What is the 9th harmonic resonant frequency of the glass? Let's solve this using GRASP. First, I labeled the diagram with the different length to wavelength ratios. At the 9th harmonic, the length is equivalent to 9/4 lambda. given and required. The length is 19.0 centimeters, so 0.190 meters. The temperature is 25.0 degrees Celsius, and since it is the ninth harmonic, length equals to 9/4 times the wavelength. Required is the frequency at the ninth harmonic. Let's analyze. We can rearrange L equals 9/4 lambda formula to solve for the wavelength. Then we can find the speed of sound in the room and solve for the frequency using the speed of sound and the wavelength. In the equation, F equals 331.4 meters per second plus temperature times 0.606 meters per second over Celsius divided by 4 length divided by 9. Then we solve for the frequency by inputting the length and temperature values. The result of this calculation is 4.10 kilohertz at 2 significant digits. Finally, let's rephrase this in a sentence. Therefore, the resonant frequency of the glass at the ninth harmonic is 4.10 kilohertz. Thank you for watching.